Hello, and welcome to the video safety presentation on physical hazards in the laboratory for the Department of Material Science and Engineering at Johns Hopkins University. The purpose of this video is to acquaint you with some of the non-chemical hazards that are commonly found in material science and engineering laboratories, particularly electrical hazards, cryogenic fluid hazards, and compressed gas hazards. Before we begin talking about those three kinds of hazards, I'd like to just quickly review the basic philosophy with regard to safety that we have in our department. And the most important point is that no experiment is really worth putting your life or your health or that of someone else in danger. In other words, safety is of the utmost importance. I believe I can speak for all of the faculty of material science and engineering when I say that we would much rather have you do an experiment safely and perhaps a little bit more slowly than push ahead without proper regard for safety or with undue haste and have an accident. All of us are personally responsible for safety in our laboratories as principal investigators, and none of us want to find out that there's been an accident in our lab in which someone has been injured or, in worst case, actually killed. Yet there are hazards in our laboratories which can injure and kill people, and so we need to be cognizant of those at all times. The corollary of this is that nothing that we do in the laboratory should be started without a proper, prudent consideration of the safety implications of that practice. And our goal, of course, is to have no incidents in which someone is injured, seriously injured, or even killed. And what goes along with that is we also don't want to accept any excuses for incidents that may occur. It's easy to look back after the fact and say, well, this was done wrong, or that was done wrong, or if this procedure had been followed, or whatever. The point here is that we can look ahead. We can foresee the potential for accidents, and we can head off those accidents before they occur if we're paying proper attention to the work that we intend to do. With that said, the three topics in this class are how to deal safely with electrical equipment, how to deal safely with compressed gases, and how to deal safely with cryogenic fluids. Virtually all of our labs involve electrical equipment of some form or another. And the primary hazard, of course, associated with electrical equipment is the risk of electrical shock. And we'll just point out that a relatively small amount of current, significantly less than 1 amp, can be fatal. Yet ordinary laboratory circuits and actually ordinary household circuits are capable of producing currents up to 20 amps. So the current in the ordinary wall sockets in your lab or in your office in your house are certainly capable of killing you. And we need to be aware of that, and we need to know how to deal safely with that current. Electrical safety is not restricted to arcane high voltages or very high current systems, such as RF furnaces and things like that. The ordinary lab current is actually very dangerous. A secondary hazard is that the presence of electrical equipment, such as motors, can be an ignition source for ignitable, flammable, or explosive vapors. So in the briefing on chemical safety, we talked about the fact that fire requires some fuel, some oxidizer, and an ignition source. And it's important to keep in mind that electrical equipment, particularly motors, can provide that ignition source. As I mentioned, it is certainly possible for electrical equipment to kill you. And as an example, I'd like to point out the unfortunate case of this man, Tyrone Mall, who was a professor at Cleveland State University in biology. He was a biologist who grew plants in his laboratory, and as a result he had grow lights in his lab. The grow lights were grounded. They had three-prong grounded plugs, but for reasons which are unclear, at least to me, he plugged a three-prong plug from a grounded, or what was supposed to be a grounded light, into one of those cheater plugs that allows you to plug a three-prong plug into a two-prong outlet. As a result, his light was not properly grounded. Under ordinary circumstances, that wouldn't be a big problem, except that there was an internal fault in the wiring of his light, which meant that the housing of the light was actually live. And he touched it, was grounded someplace else through his body, and was electrocuted and died. So these sorts of things can happen, and they can happen in academic labs. This is not hypothetical. So how do we minimize those electrical hazards? Well, the first thing is we inspect wiring on all of our equipment frequently. And if we notice that any wiring is damaged or frayed, those have to be replaced right away. Those are an imminent hazard that need to be paid attention to. Secondary concern is to know the location, operation of shut-off switches and circuit breaker panels. This is so that if someone is electrocuted or is receiving an electrical shock, someone else in the lab can turn off the power without risking themselves. Extension cords are for temporary use only, right? So you can plug in an extension cord and use it for, a portable piece of equipment. But if you find yourself in a situation where a permanent piece of lab equipment needs to be powered and you have it plugged into an extension cord, then you should really talk with your principal investigator about either moving the equipment to a place where it can be plugged directly into an outlet, or having an outlet placed in a location where the equipment is, so you don't need to use the extension cord. Water and electricity, of course, don't mix very well, so we want to minimize the potential for water to come in contact with electrical equipment. And in this regard, it's important to note that this can be due to leaks, for instance, in cooling water lines, but it can also be due to condensation. Of course, Baltimore summers tend to be quite humid, and that can lead to condensation, particularly on cold water lines in the summertime, and those leaks can create a shock hazard. Any live part of an electrical equipment which is at any significant voltage, say above about 50 volts or so, should have guards on it so that someone cannot come in contact inadvertently with that potential. With regard to personal electrical safety, of course, goes without saying that we avoid contact with live electrical circuits. Service, if it's necessary on a live circuit, should only be done by qualified individuals. Whenever possible, of course, power should be disconnected before servicing any sort of equipment. And it's also important to note that many pieces of equipment have capacitors internally that can store significant amounts of charge well after the equipment is turned off or disconnected from power. So you need to be aware of that. If it is necessary to handle energized equipment, then you should be sure that your hands are dry. Use non-conductive gloves if possible, and or rubber-soled shoes to prevent yourself from being inadvertently grounded. And if possible, you should work with one hand. The old saying is one hand for the ship and one hand for yourself. That minimizes the chance that you'll have an electrical current which can travel up one arm and down the other through your chest cavity, affecting your heart. Finally, as I mentioned earlier, if someone is in contact with a live conductor and is being electrocuted, it's extremely important that you shut off the power first before attempting to hurt that person. If you touch a person who's being electrocuted, it's possible for you to become part of the conductive path and be electrocuted yourself. Okay, let's move on now to compressed gases. Compressed gases are commonly found in our laboratories. Often they're inert gases such as nitrogen or argon, but they can be other things. For instance, oxygen is commonly used, and flammable gases can be used as well. The primary hazard of compressed gases that we'll talk about today is the existence of high pressure. This creates a high amount of stored energy, which is potentially stored kinetic energy in the compressed gas cylinder, with potentially catastrophic consequences, as I'll talk about in a second. A related hazard that we shouldn't lose sight of, however, is asphyxiation. That is, even something which appears to be innocuous, such as helium or nitrogen or argon, can be dangerous because it can displace oxygen and actually cause you to pass out relatively quickly. If we're talking about flammable gases, and of course fire and explosion are a concern, corrosive gases are sometimes used, and they create the potential for chemical burns. And from time to time we use toxic gases, which of course create the potential for poisoning. What I'd like to do next is show you a segment of video from actually one of my favorite TV shows called The Mythbusters. And this is going to illustrate this hazard of high pressure. It's a item of folklore in laboratories that if you have a compressed gas cylinder and you knock off the valve on the top of the cylinder, that the compressed gas will be released very suddenly, and that cylinder becomes essentially a torpedo that can go through a wall. And the Mythbusters actually tackled this particular issue. And I'd like to show you that video to show you the result.
High-pressure gas cylinders have been around for 100 years, and legends of their destructive potential have been around for 99. But could a ruptured tank really burrow through a brick wall? Into the next county.
Here we go, shearing the regulator off a tank. Attempt number 2. In 5, 4, cross your fingers, 3, 2, 1. is a lovely, lovely sound.
The valve has sheared clean off, and that's a very good sign. It looks like the cylinder flew straight and true, but did it have enough thrust to crack the wall?
Oh, God. It was the lard that did it.
At 40 miles per hour, the air tank turned the cinder block to cinders. It even put a fair dent in the wall 6 feet behind it.
It totally.
way.
I mean, it didn't go all the way through, but it went through this one, and it was going. It's working its way through that one.
I was ready to see this as not possible. I was totally expecting it not to actually work, because it's one of those apocryphal tales, and everyone we talked to had heard the story, but no one knew anybody that it happened to.
You know, this was an optimum situation for this tank. What this tank did is as good as it gets.
My favorite thing is just the perfect roundness of the top of this hole. It also pushed this entire wall back a half an inch.
Although the cylinder was deliberately aimed, you couldn't ask for a more convincing result. So let's call this myth totally and spectacularly confirmed.
Well, there you have it. Compressed gas cylinders really do present a serious hazard in the lab. If the cylinder valve should be knocked off, as you just saw, that cylinder can become a torpedo and can obviously cause significant damage to the lab and to any individuals who might be unfortunate enough to be in its path. As a result, there's a number of handling precautions that we always take when dealing with compressed gas cylinders. One of the most important rules is that we always keep the cap on the cylinder until the cylinder is secured and it's ready for installation of the regulator. This minimizes the chance that if something should happen to the cylinder, if it should be knocked over or fall, that the valve would be knocked off. We always store cylinders upright, never lying down on the floor, and they always must be secured with a chain or a strap to a wall or other fixed object, such as a lab bench. We should never see in the lab a cylinder simply standing upright without being secured with a strap or a chain. When you're moving a cylinder, you should always use a cylinder cart for transporting it, even for short distances, a few feet across the lab. You just don't want to take the chance that you'll drop the cylinder and have it become a torpedo like you just saw. Well, corollary of that, of course, is that we never move gas cylinders unless the cap is actually in place. It's worth spending a second talking about the proper way to use a compressed gas cylinder. There's a number of steps which may be unfamiliar to you if you've never used a compressed gas cylinder before. The first thing is, when you get a compressed gas cylinder in your lab and it's been secured to the wall or to a lab bench, the first step is to remove the cap and then attach a closed regulator of the proper type to the cylinder. And here it's worth noting that different kinds of gases use different kinds of regulators, and in order to minimize the chance for confusion between regulators and gas, the threading and the fittings on different regulators, various regulators, are appropriate for the kind of gas that they were intended. So a golden rule is don't try to force the wrong regulator onto a particular gas cylinder. If it's not attaching easily, there's probably a reason, and that reason is quite likely that you have the wrong cylinder for the gas that you want to use. There's a pressure adjusting screw, which I'll show you on the next slide, which you want to turn counterclockwise until it turns freely. And this is perhaps counterintuitive. We're used to valves where we turn them clockwise to close and counterclockwise to open. But the pressure adjusting screw works in exactly the opposite way. If you turn it completely counterclockwise until it spins freely, then the output pressure will be zero. And we'll talk about that again in a second. The cylinder shutoff valve can then be opened slowly. That allows the gas to flow into the regulator. And then with the output valve closed, you can turn the pressure adjusting screw now clockwise to increase the output pressure until the delivery pressure that you want is reached. And then finally you can open the output valve and allow the gas to flow to your experiment. When you're finished, you should close the cylinder valve and release the pressure in the regulator before removing the regulator from the cylinder. And a final point, which is often ignored or neglected, is that you want to leave a little bit of gas in the cylinder. That is, you don't want to run the cylinder until it's completely empty. You want to leave about 25 psi in the cylinder. And the reason for this is to avoid contamination of the cylinder with atmosphere, which can be a bad thing, particularly when you are talking about cylinders that may contain reactive gases. Here's a photograph of a typical dual-stage regulator mounted on a compressed gas cylinder. So here's the cylinder, here's the cylinder valve. This is the pressure adjusting screw, which I mentioned earlier. Here's the output valve. And this particular regulator has two gauges on it, one of which measures the cylinder pressure, or the pressure inside the cylinder, and the other one of which measures the output pressure. So again, the way in which you deal with this is with the cylinder valve closed and with the output valve closed. You would attach the output valve, the regulator to the cylinder. You tighten this fitting right here. You can completely open the pressure adjusting screw, that is, turn it completely counterclockwise until it spins freely. That will make the output pressure 0. So at that point you can open the cylinder valve. That will allow gas to flow into the first stage of the regulator. The cylinder pressure gauge will then read whatever the pressure is of the gas in the cylinder. But the output pressure will still be 0. Then you can turn the pressure adjusting screw clockwise. That will increase the pressure in the second stage of the regulator until the dial reads whatever output pressure, delivery pressure you want. And then finally at that point you can open the output valve and allow the gas to flow to your experiment. Okay, let's move on now and talk about cryogenic fluids. The hazards associated with cryogenic fluids are basically two of the big ones. The first is the possibility of a pressure buildup leading to an explosion, similar in some ways to the compressed gas pressure release that we saw a second ago. In this regard, it's worthwhile to note that when a liquid vaporizes, there's a huge volume expansion associated with that. It's a factor of about 650 times for liquid nitrogen going to gaseous nitrogen. And obviously, if that's in a sealed container, that can lead to a huge buildup of pressure and therefore explosion of that container. So we never want to seal containers completely that have cryogenic fluids in them. We always want to make sure that there's a way for that pressure to be released. A second hazard is frostbite. Obviously, cryogenic fluids are at very low temperatures, and if they are splashed onto your skin or into your eyes, there's a possibility for significant tissue damage by frostbite. Asphyxiation is also a potential hazard. If you release a large amount of inert gas simultaneously, it will displace oxygen from the atmosphere, and if you displace enough of the oxygen, then you can pass out very quickly, much more quickly than you might think. One risk or hazard of inert cryogenic fluids, which we don't sometimes think about, is the risk of fire, particularly with regard to certain organic compounds. And the reason is that the low temperature associated with the cryogenic fluid can cause enrichment of the atmosphere with oxygen, or it could actually cause oxygen to condense out of the atmosphere, and that can then create a very oxidizer-rich environment with then the right fuel and the right ignition can lead to a fire or even an explosion. And finally, if cryogenic fluids are poured onto or incident on structural materials, including many metals or actually in particular many polymers, that can cause them to become brittle and therefore fail, and that poses a risk as well. Again, to show you that these sorts of risks are not hypothetical, I'd like to tell you about an incident that occurred in February of 2006 at Texas A&M University. In particular, what happened was there was a liquid nitrogen cylinder in the chemistry department there. It exploded violently because both the relief valve and the rupture disc, which are designed to prevent the buildup of dangerous pressures in the liquid nitrogen cylinder, they had both been replaced by someone unknown with brass plugs, which obviously did not allow the pressure to be released gradually, and therefore it exploded violently. Fortunately for the people in the lab, the explosion actually happened at about 3 o'clock in the morning, and there was no one in the lab. Here's a photo of the cylinder itself that underwent the explosion. What actually happened in this particular case is there's actually you can't see it here, but there's sort of a cylinder inside a cylinder. The inside cylinder leaked into the wall, into the void between the inside cylinder and the outside cylinder. That's where the pressure buildup occurred. The ends of the cylinder then were not able to contain that pressure, and as it happened, the lower end of the cylinder failed first. That launched the cylinder vertically upwards until it hit the ceiling of the lab in which it was. So you can see that the bottom of the cylinder is gone. The top end of the cylinder has been smashed, and it's hard to see a little bit in this photo, but there's actually a bunch of ripples due to the compression of the cylinder as it hit the ceiling of the particular lab. At this point, what I'd like to do is actually read for you from the report by the engineer who investigated the aftermath of the incident, and it reads as follows. The cylinder had been standing at one end of a 20-foot by 40-foot laboratory on the second floor of the chemistry building. It was on a tile-covered 4 to 6 inch thick concrete floor directly over a reinforced concrete beam. The explosion blew all of the tile off the floor for a 5-foot radius around the tank, turning the tile into quarter-sized pieces of shrapnel that embedded themselves in the walls and doors of the lab. The blast cracked the floor, but due to the presence of the supporting beam which shattered, the floor held. Since the floor held, the force of the explosion was directed upward and propelled the cylinder, without the bottom, through the concrete ceiling of the lab into the mechanical room above. There it struck 2 3-inch water mains and drove them and the electrical wiring above them into the concrete roof of the building, cracking it. The cylinder came to rest on the 3rd floor, leaving a neat 20-inch diameter hole in its wake. The entrance door and wall of the lab were blown out into the hallway. All of the remaining walls of the lab were blown 4 to 8 inches off of their foundations. All of the windows, save one that was open, were blown out into the courtyard. So here are some photos of the aftermath of the explosion. This is actually in the lab where the explosion occurred. You can see that here's the place where the cylinder was. You can see, as the report mentioned, that the tile has been completely removed, and you can see some shards of tile lying around in various places and embedded in the wall in a few places. Here's one wall of the lab which was nearly completely blown out. Here's another section of the lab, obviously with heavy damage. Here's the hallway outside the lab, and again you can see the wall of the lab has been pushed out into the hallway. Unfortunately, I don't have any photos of the damage to the ceiling or damage to the mechanical room above this particular lab. So with that as a cautionary tale, how do we work safely with cryogenic fluids? Well, the first thing is to use only in well-ventilated areas. This is to reduce the danger associated with asphyxiation. We should only use cryogenic fluids in specially designed containers known as Dewars. These Dewars are designed such that it is not possible to trap or completely seal the cryogenic fluid in the container. There's always a pressure relief mechanism to prevent an explosion. What goes along with that is that we should never seal or allow to become sealed a cryogenic fluid in a container. Right? And you have to be a little careful. Of course, you need proper maintenance of your containers and your Dewars. As I mentioned, for the cylinder at Texas A&M, someone unauthorized, without apparently understanding the risks associated with what they were doing, had replaced the safety devices, the pressure relief valve and the rupture disc, with brass plugs, and that's what allowed that pressure to build up in that case. But pressure can also build up in sort of unexpected ways. For instance, if you get condensation that freezes, it might freeze off a vent, and it's possible for pressure to build up for that reason as well. We always want to handle cryogenic fluids carefully to avoid frostbite. We don't want to have cryogenic fluid splash on our persons. One of the big risks is if you take a cryogenic fluid and then you fill a warm container. Of course, as you do that, there's going to be a lot of splashing until the warm container cools down to something close to the temperature of the cryogenic fluid. So you always want to fill containers slowly to minimize that kind of splashing. Whenever we're working with cryogenic fluids, we want to use the proper personal protective equipment. So we want to cover exposed skin. An ordinary lab coat or shirt or pants is fine. Closed-toed shoes, as always in the lab, because cryogenic fluids commonly spill onto the floor and can spill onto our toes. We want to wear proper gloves. There are special insulated gloves for dealing with cryogenic fluids, which we should always wear when transferring fluids from one container to another. And finally, you always want to wear eye protection, because if there's one place in your body where you don't want to splash a cryogenic fluid, it's into your eye. And in particular, if you're pouring a cryogenic fluid with the attendant risk of some splashing, then a face shield, a full face shield, is strongly recommended for that process. In summary, there's a variety of non-chemical hazards that can exist in our labs, and as we've seen, these include electrical hazards, compressed gases, and cryogenic fluids. The key is to know and understand the hazards associated with the equipment or the materials that you're working with, and the procedures for minimizing those hazards, and as well as the proper protective equipment to wear. This briefing provides only a quick summary of the hazards and the proper safety techniques for dealing with those hazards. You will receive more detailed training in your individual lab, which you should take to heart. And finally, as I always say, there is no substitute for personal responsibility in the lab. Even after you've been trained, there cannot always be someone looking over your shoulder to make sure that you're following the proper techniques or that you're not doing something either on purpose or inadvertently that might create a hazard. So you should always ask if you have any question about whether or not what you're about to do is safe. In the case of the incident at Texas A&M, if the student or whoever it was that replaced the pressure relief valve and the burst plate with brass plugs to simply ask someone if that was a safe thing to do, he or she would have found out probably that it was not a safe thing to do, and that incident could have been avoided. So you have to take responsibility for the things that you do, and you should not be afraid to ask questions. You can ask questions of the other members of your lab group, you can ask your principal investigator, and of course you can also come to me as safety officer for the department. With that, I thank you for your attention, and I ask you to always be safe in the lab.